Imagine a world where electricity flows with zero loss. No energy is wasted as heat. This is the promise of superconductors. These remarkable materials have the potential to revolutionize our world. From faster computers to more efficient power grids, the possibilities are endless. Superconductors could usher in a new era of technological advancement. The impact of superconductors on technology cannot be overstated. They have the potential to transform industries like transportation, energy, and medicine. Imagine levitating trains that travel at incredible speeds powered by magnetic fields. Picture medical imaging devices that are more sensitive and precise than ever before. These are just a few examples of the transformative power of superconductors. Superconductors could also help us address some of the world's most pressing challenges. Climate change, for instance, is driven in part by energy loss in power grids. Superconductors could drastically reduce these losses, making our energy systems more sustainable. They could also enable the development of new renewable energy technologies such as fusion power. The development of room temperature superconductors would be a game changer. It would pave the way for the widespread adoption of this technology, ushering in a new era of technological progress. The future is bright for superconductors, and their impact on our world is only just beginning to be felt. Superconductivity is a fascinating phenomenon that occurs at extremely low temperatures. In normal materials, electrons flow through a lattice of atoms, encountering resistance along the way. This resistance causes energy to be lost as heat. However, in a superconductor, something extraordinary happens. At extremely low temperatures, electrons in a superconductor pair up. These pairs, known as Cooper pairs, move through the material without any resistance. Imagine a crowded dance floor where people are constantly bumping into each other. Now imagine the dancers pairing up and gliding effortlessly through the crowd. This is analogous to what happens in a superconductor. This absence of electrical resistance has profound implications. It means that electricity can flow through a superconductor with no loss of energy. This property has the potential to revolutionize many technologies from power transmission to computing. Moreover, superconductors exhibit another remarkable property called perfect diamagnetism. This means that they expel magnetic fields from their interior. If you bring a magnet close to a superconductor, it will levitate. This phenomenon has captivated scientists and the public alike, and it has led to the development of technologies like maglev trains. The discovery of superconductivity dates back to 1911. Dutch physicist Heike Kamerlingh-Onnes was studying the electrical resistance of mercury at extremely low temperatures. To his astonishment, he discovered that the resistance abruptly dropped to zero at a temperature of 4.2 Kelvin, or negative 268.95 degrees Celsius. This groundbreaking discovery marked the beginning of superconductivity research. In the following decades, scientists discovered other materials that exhibited superconductivity at similarly low temperatures. These early superconductors were primarily metals and alloys, and their critical temperatures remained stubbornly close to absolute zero. However, each new discovery brought with it a deeper understanding of this remarkable phenomenon. A major breakthrough came in 1957 with the development of the BCS theory. This theory, named after its creators John Bardeen, Leon Cooper, and John Schrieffer, provided a theoretical framework for understanding superconductivity. It explained how electrons form pairs at low temperatures and how these pairs move through the material without resistance. The search for superconductors with higher critical temperatures continued throughout the 20th and 21st centuries. In the 1980s, a new class of materials called high-temperature superconductors was discovered. These materials exhibit superconductivity at temperatures above 77 Kelvin, which is the boiling point of nitrogen. This discovery opened up new possibilities for practical applications of superconductivity. While superconductors offer tantalizing possibilities, they are not without their limitations. One major limitation is their critical temperature. This is the temperature below which a material exhibits superconductivity. Above this critical temperature, the material behaves like a normal conductor, exhibiting electrical resistance. For many years, the critical temperatures of superconductors remained very low, close to absolute zero. This meant that they could only be used in specialized applications requiring expensive and complex cooling systems. However, the discovery of high-temperature superconductors in the 1980s offered hope for more practical applications. Another important factor limiting the use of superconductors is their critical magnetic field. This is the strength of the magnetic field above which a material loses its superconducting properties. When a superconductor is exposed to a magnetic field stronger than its critical field, it ceases to be a superconductor and behaves like a normal conductor. The critical magnetic field is another factor that must be considered when designing applications for superconductors. For example, superconducting magnets used in MRI machines must be carefully engineered to operate below their critical field strengths. Despite these limitations, superconductors have found a wide range of applications in various fields.